happens when you throw a ball up in the air. It always comes down, doesn't it? It doesn't continue flying up, and away into outer space. In fact, you'd have to work really hard to even get that ball up into outer space. Why is this? This is because the planet Earth has what is called a gravitational force. This gravitational force, also called the G-force, is the force that pulls or attracts all physical objects towards the center of our planet. And actually, it's not just the Earth that has a gravitational force. We mostly focus on the G-force of planets, but all physical objects have a certain amount of gravitational force to them. That's right, even you yourself have a certain amount of gravitational force that attracts other objects to you. We don't see it because the Earth's gravitational force overpowers anything we have and any similar force we experience from smaller objects. Gravity is a force that attracts objects of mass towards each other. This gravitational force is the force that causes things to accelerate. So it is the G-force that gives you the amount of acceleration caused by gravity. When you place a marble on the side of a hill, you'll see the marble begin to accelerate as it makes its way down to the bottom. That's gravity at work. There is actually a formula you can use to help you calculate this gravitational attraction of any object. G equals gm over r squared. The little g stands for the amount of acceleration that is caused by gravity. This is what's commonly referred to as G-force. The big G is the Newton's gravitational constant, approximately 6.67 times 10 to the negative 11th power newtons m squared per kilogram squared. The little m stands for the mass of the object and the r stands for the radius of the object. Usually you'll calculate the G-force for large spherical objects like planets. You can calculate the G-force that your own body puts out by approximating your body with a little sphere. But you will see that this force is very tiny when you compare it to the G-force of planet Earth. To use this formula to calculate the G-force of planet Earth, you'll input the mass of planet Earth along with its radius. The gravitational constant G remains the same no matter where you are in the universe as calculated by Isaac Newton, approximately 6.67 times 10 to the negative 11th power newtons m squared per kilogram squared. Now, you might be wondering how in the world you're going to find out what the mass of the planet Earth is. But not to worry. This has already been done. Actually, this has been done for the radius of the planet Earth too. Here are the numbers. Earth's mass is 5.97 times 10 to the 24th power kilograms, while its radius is 6.38 times 10 to the 6th power meters. You'll use these numbers in your equation for G-force and plug them in for the m and for the r. Let's evaluate it and get our answer. Using the equation G equals gm over r squared and plug in our values, 6.67 times 10 to the negative 11th power newtons m squared per kilogram squared, all times 5.97 times 10 to the 24th power kilograms, with all of that divided by 6.38 times 10 to the 6th power meter squared. This equation gives you a G-force of 9.8 meters per second squared. This means that if you drop something from the top of a high-rise, your object will fall with an acceleration of 9.8 meters per second squared. This number for the acceleration caused by gravity is the number used in most physics problems that you'll come across. Now, if you are asked to find the G-force of other objects besides planet Earth, all you need is the mass of the object and its radius. Let's look at an example. Say you want to find the G-force of the planet Jupiter. To find your answer, you'll need to know the mass of planet Jupiter and its radius. According to NASA, Jupiter has the following specs for the mass and radius. Its mass is 1,898.19 times 10 to the 24th power kilograms, while its radius is 71.49 times 10 to the 6th meters. Plugging these values into the G-force formula and then evaluating, you get this. 6.67 times 10 to the negative 11th power newtons m squared per kilogram squared times 1,898.19 times 10 to the 24th power kilograms, which is all divided by 71.49 times 10 to the 6th meters squared. So the G-force on planet Jupiter is approximately 24.8 meters per second squared. Comparing this to planet Earth's G-force of 9.8 meters per second squared, you see that Jupiter has a higher gravity. This is to be expected since Jupiter is a much bigger planet. The larger the object, the larger its g-force. The g-force is the gravitational force of a planet. It tells you the amount of acceleration caused by the gravity of the planet. This is what causes things to fall and stay on the ground. Actually, it's not just planets that have a g-force. Every single physical object has a certain amount of g-force to it. To calculate this g-force, use this formula. The little g is the g-force or the amount of acceleration caused by gravity. The big G is Newton's gravitational constant, approximately 6.67 times 10 to the negative 11th power newtons m squared per kilogram squared. The little m is the mass of the object and the little r is the radius of the object. To find the g-force of the object, just plug in the object's mass and radius. If your units of mass are kilograms and your units of radius are meters, then your g-force will be units of meters per second squared.